Hello, welcome back. Today I'm going to cover the first part of Chapter 2. So we're going to go over these elements. And the first thing we're going to look at is our data types. When you're in programming, one of the things we need to be able to do is store numbers and characters and text. And in order to do that, we need to make things that are called variables. And a variable is basically a data container that will have a specific type, and a given type of variable is used to store data. The types of variables that we can store in C++ include a char, which is a single character, an int, which is a whole number, basically a number without any decimal portion, a floating point number, which is a decimal number with up to 6 to 7 digits of precision, a double, which has twice that amount of precision, a void, which is actually a unique type of variable, or type. It's really it represents nothing, which is distinct from the number 0. And in programming, this is a very important concept. There are instances where you don't want to store the number 0. Instead, you want to store the fact that you have not collected data yet. So that's what the void would be used for. The Boolean it's actually a number that stores the values 0 and 1, which are then used to represent the values of true and false. And then we have a wide character, which holds 16 bits. And this is also known as Unicode. When computers were initially created, the char was created that could store up to 256 characters. But then as computers were used more widely around the world, we had to accommodate many more character sets. So an 8-bit char is not sufficient to store all the world's characters or alphabets, but a 16-bit number is, and has enough to store the alphabets from multiple languages. So think of the data type as a label that tells the compiler what type of data is going to be stored in a variable. And the variable is really the place in memory, and it has a name. So a program needs to know both pieces of information in order to store information in the computer's random access memory. Now you can imagine if multiple people were making C++ compilers and they didn't have a standard to build their data types, they might build all sorts of data types. The International Standards Organization sets the standards for C++ and have defined what the standard types are for C++. So no matter which compiler you use, you will use the same data type. So if we look at this chart, we can see that we can represent numbers with binary bits. And the truth is that in a computer, it only has one data type at the machine level, and that's ones and zeros. In order to make larger numbers than 0 and 1, the computer will combine multiple bits in order to be able to represent multiple numbers. So if you only had 1 bit, you could store the number 0 or 1. If you had 2 bits, you could store the numbers 0 and 1, but you could also represent a 2 and a 3 just by changing a different combination of bits. So if they're both zeros, that would be a 0. If the first bit was flipped over to a 1, that would be a 1. But then, since you're binary, you only have 2 digits, so you make the next position be 1, and then the 0th position goes back to 0, and that represents 2. So 1, 0 in binary is actually the number 2. And then if you then add 1 to that, you get 1, 1, which is the number 3. So 2 bits allow you to store up to 4 numbers. 3 bits will allow you to store 8 different values. And following the same logic, 8 bits will allow you to store up to 256 combinations. And notice that the highest value here is 255 because we start at 0. So this shows you the possible combinations. Now, one of the conventions that can be done with binary numbers is we can say that the first most significant bit will be a signed bit, and if it's set in one direction, it'll be negative, and if it's set in another direction, it'll be positive. So with 8 bits, we could store either 0 to 256, or we could have that represent minus 128 to 127. And with 16 bits, it could be minus 32,768 to positive 32,767, and so on and so forth. So often we have to make a distinction between types that are signed and types that are unsigned. There are also other modifiers in C++. You have short, long, and unsigned. And when you combine all these together, you get all these different types that we can store in C++. A regular char would be minus 128 to 127. An unsigned char would be 0 to 255. A signed char is minus 128 to 127. So that's kind of interesting. Why is a char representing a number? Well, even though a char represents a character, it's actually stored numerically in memory. So we have numeric values for the char. For our ints, we can see that we can have a regular int uses 4 bytes of memory. A short int uses 2 bytes of memory. And you can see that there's corresponding less precision that you can store in a short int versus a regular int. An unsigned short int, notice it's from 0 to 65,000 versus minus 32,000 to positive 32,000. An unsigned int is the same as a regular int, except that it doesn't store negative numbers. And then a long int, interestingly enough, the long int is identical to the regular int. So really, if you say int, by default, it's a long int. Unsigned long int basically is the same as an unsigned int. Then we also have our floating point types that allow us to store decimal points of precision. The float, you'll notice, stores 6 digits worth using 4 bytes. And a double, about 10 digits worth, about 8 bytes. It doesn't end up exactly at 6 digits or 10 digits because it depends on where the number sits, when you convert from binary to decimal. But roughly speaking, that's the precision you can get with a 4-byte float or an 8-byte double. And then a long double is 10 bytes. And this is used when you need a lot of precision. Often when you're working with money, you might want to do that. So why is it important to be careful about our types? Well, one reason is we want to use the minimum amount of memory necessary to store the information we're storing. So generally speaking, you will pick the smallest type that will store the information you need. So if you're only working with whole numbers, there's no reason to use a float. You would use an int. And if the largest number you had was, say, somewhere less than 255, probably rather than int, you might use a short int, or you might use even an unsigned char, depending on what numbers you needed. So you need to look at the value you're storing and pick the right type based on the value you're storing. Why is it not important to make sure we get this right? Well, on June 4th, 1996, there's an unmanned Ariane 5 rocket that was launched by the European Space Agency, and 40 seconds later it exploded. And why did that happen? Well, there was a programming error. A 64-bit floating point number relating to the horizontal velocity of the rocket was converted into a 16-bit signed integer. So there's a couple things that could happen here. One, well, we're going from a floating point number to an integer, so maybe we'll lose some precision. But that wasn't the big problem. The big problem was that the number that they're converting in was larger than 32,767, which is the largest that a 16-bit number can store. And what happens is that when you exceed the size of the number that goes in binary it truncates. And what ended up happening here is that 32,767 turned into which is a large positive number, very quickly was instantly turned into a large negative number. The rocket thought that it was going in the wrong direction and proceeded to do a 90-degree turn at roughly Mach 6 or 60 or whatever speed a rocket's going at that point. And oddly enough, the structure could not withstand that, so it tore apart and exploded. And this is a video.
Attention pour décompte final.
A final decision to go was taken.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, feu. Allumage. Décollage.
So at this point, everything's going normally. The rocket's lifting off, and you can see that it's starting to pitch over, and there's a horizontal velocity component. When that got to a certain point, that's where the software suddenly thought it was going in the wrong direction. And watch what happens to the rocket, the way it moves. See that suddenly pitch over? That's where the software
37
made the
seconds
mistake.
into the launch, the onboard computers decided 501 was 90 degrees off course.
If you do the math and do some vector math and change the direction of your X component, you'll see that that turns into a 90-degree turn.
They made an automatic adjustment to the trajectory as the rocket was traveling at the speed of sound.
Automatic adjustment means code, programming. So, we can see that there can be very serious consequences to some of the code we write. And as programmers, we need to be aware of what we're programming, and if it's something critical, testing is vitally important. So let's don't go to Socrative.com. That's what I present in the class. After I read this question, pause, think about the answer, and then I'll give you the answer after you've paused the tape. So you're programming a solution for a warehouse. You need to store data representing the weight of items in a storage bin. They only need the weight to 2 digits of precision. What data type will use the minimum amount of memory? So think about that. Pause the tape if you need, the video if you need to, and then I'll give you the answer. So the answer is most likely a float. You know, they need 2 digits of precision, so they need something that can store a decimal. An int can only store a whole number, so an int won't work. A double could do it. It can store a decimal, but it's way overkill. It's twice as big as we need it to be for sure. And a Boolean only stores 1 and 0. That's clearly not going to be good enough. So the answer is a floating point number would probably work best. So let's say you're developing a program that needs to store an integer that might be between 0 and 60,000. What is the type that will satisfy this requirement and use the minimum amount of memory? So pause, think about the answer. And let's see, 0 to 60,000. Well, an int, might work. This is only storing integer values, possibly a short int or a long int. Of course, we know that an int and a long int are the same thing, or an unsigned short int. Well, it only needs to store between 0 and 60,000, and it doesn't need a negative number. So I'm kind of thinking the unsigned. And if we look at our chart, let's see, 0 to 65,000. Unsigned short int should be large enough to store 0 to 60,000. So sometimes you need to look at the chart. So the answer here would be unsigned short int. So now that we know what the different types are, how do we use those to declare variables? Well, a variable declaration is a statement that must have a data type and a variable name. And the basic format is you provide a data type, and then which has to be one of the keywords we identified. And then the variable name can be anything you want it to be. In general, when you're declaring a variable name, you want it to be meaningful. And it's not unusual to use compound words. And the way you can use that is you can use an underscore to separate the variable name. Or you can use compound words where the first letter is capitalized. Usually with variables, we would start off with a lowercase, and then the second, if we have another name in the compound name, another word in the compound name, we capitalize that. So there's a couple ways of doing that. We'll show that later. But that's the variable name is a name you pick. So here we have some examples of declaring some variables. The first three are floats, and so the type is float. Then we have the variable name, and then you notice a semicolon. So all your statements in C++ will be terminated with a semicolon. Initially, when you're programming, you will forget semicolons on a regular basis. So get used to looking at your lines and seeing if you find them. Often the compiler will give you an error message that says expecting a semicolon, and then that's where you'll look through the lines and find them. The last two are integers, and we can see that, based on the variable names, it kind of makes sense why those types are picked. Balance, you're talking about money. Typically, there's going to be a decimal portion to any financial transaction. So balance, deposit, or withdraw should be a floating point type. And then transaction count or check number. Well, you can't have half a transaction, so that suggests a whole number or an int. And check numbers, most people's checks don't have checked, check 450.5 or something like that. It's always a whole number. So the type of information you're storing dictates which type you should pick. Now, once we have a piece of memory to store things in, then the question is, how do I put values into that variable? Well, one way is you can declare your variables beforehand, and then later on in your program, you can then assign values. And the way we assign values is with the equal sign. The temptation is to say AVE equals 35.29 or num equals 5. But really, the equal sign, I'm going to ask you to think of it as assigned into. So in this instance, we declared a floating variable, and later on, we assigned 35.29 into the variable AVE. You can also declare the variable and assign a value into it all in one line. So both approaches are valid. Another thing you can do is you can declare multiple variables all on one line using one type keyword, as long as all of those variables are going to be of that type. So here we declared money and speed, and both of them are doubles. And another thing you can do is you can actually do chained assignment operations. And the way these work is the assignment operator, it goes from left to right. And so the first operation that's done is 0.0 is assigned into speed. And then speed, now having 0.0, is assigned into money. So this will initialize both speed and money to 0.0. So these are different ways you can do assignments. As a beginning programmer, I recommend just using the first two formats at the top, either declaring a variable and then later assigning into it, or declaring a variable and assigning directly into it at the same time. But I don't recommend this last thing. It makes code harder to read, and it doesn't change the execution speed of your program if you declare your variables all on separate lines. So our variables, the name of the variable is called an identifier. And identifier is the name of a user-defined object. We're going to use identifiers to name our variables, but later on we'll use them to also define functions. And later on, after that, when you take the next semester class, you'll learn to define things that are called classes. And then there are these items called labels. So, but for this course, we're going to use them primarily for variables and functions. And there's some rules to defining identifiers. Identifiers can contain the letters capital A through Z, lowercase a to Z, the numbers 0 to 9, or the underscore. And that's it. You can't use any special characters with your identifiers. Another rule is that the first character of your identifier must be a letter or an underscore. You can't start a variable name with a number. The processor the compiler will try to make that into a number. When it reaches a character, it gets confused. So always start with a character or an underscore. And so no special characters, and keywords can't be used as variable names, which makes sense because if you have a keyword, the compiler is not going to look at that as a variable. It's going to use it as a keyword, and often these errors are very odd and hard to understand. Identifiers may be any length, but only 1,024 characters are significant. That's a lot of characters. And so one of the recommendations is that feel free to make fairly verbose identifiers that make it easy to understand what your variable is. So rather than L for a variable that's going to represent length, actually use the full word length. Rather than N for first name, use the compound word first name. And typically with variables, you're going to make the first character lowercase and any subsequent compound words uppercased, and that's called camel casing. So let's look at how these naming rules apply. So balance, that's a valid variable name. It's using characters, the appropriate characters, and will work just fine. Transaction amount, it's invalid. If you're going to use compound words, you can't have a space between the compound words. The compiler will read transactions variable, and then they'll see this other thing, and it won't know how to deal with that. So that will actually cause the syntax error. So you can't have a space. This one is invalid because of the number sign. You can have the underscores, but the number sign is a special character and can't be used for variable names. My money is a perfectly valid a variable name, or will work for the compiler. I generally recommend that you start your variables always with a lowercase, however. Case, that's invalid because it's a keyword. There's actually a command called case, and when the compiler gets that, it's not going to read that as your variable. It's going to treat it as a keyword, and then it'll be confused because probably it won't be a properly formed case statement. Case is valid with a capital C because in C++, C++ is case sensitive, so it's going to treat the capital C case as different from the lowercase c. So there's a keyword which has a lowercase c, but there isn't one which has an uppercase c. So you could do that. Although, again, I prefer my variable names to start with a lowercase. If there's a function name, that might make sense. And then this one's invalid because it starts with a number. Auto is invalid because it's a keyword. And my auto is valid, although, again, I prefer lowercase to start for a variable name. So where can you declare your variables? Well, you can declare them inside a function, outside a function, and in a function header line. We're going to learn more about functions later on. If you did the Hello World application, then you know that main is the first function that you have in a program. And so you can declare your variables inside that function or outside. And where you declare it dictates what parts of the program you can see it, and that's called the scope. So if you declare a variable inside a function, then it can only be seen from code that's inside that function. If you declare it outside of all functions, that's called a global variable. and it can be seen anywhere. For this course, we're going to ask you to never use global variables. There are problems with using them. There's efficiency problems with them, and so generally speaking, when we declare variables, we're going to always want to declare them inside a function or inside a function header line when we declare the function, but never outside of a function. When you declare a variable, C++ does not default it to a default value. For example, you might think that a variable would always default to 0 when you first declare it. You can't depend on that. You must always initialize your variables if it needs to have a starting value. It's not a bad practice to always initialize your variables, but it's not necessary to do that as long as it's initialized before you use that variable for something. So if you want to output it to the screen, make sure that it is initialized before it's output to the screen. If you're passing it to a function or using it in a calculation, it needs to be initialized before that happens. And when you compile a program, if you don't initialize a variable before use, it will give you these warnings. Local variable used without having been initialized. If you see that, it means you probably need to find some spot before that line of code, and these are the lines of code, and find a place to initialize it before it gets used. Otherwise, you might get something like this, 85 kajillion days on the road driving minus 9 to the kajillionth power mile per hour. Okay, well, that code obviously has a problem. There's also a term called L value and R value, and really that's just a way of talking about formula. And so an L value is something on the left side of the assignment operator, on the left side of the equals, and an R value is something on the right side. In programming, the L value or left value on the left side of the assignment sign cannot be, it can't be a literal value. It has to be a variable. We can't assign X into 5.2 because 5.2 isn't a space in memory. It's an actual value. This code is actually written backwards. It should have been X equals 5.2. And then similarly, here, square root open parentheses X, that's actually a function call. You can't assign a value into a function call. Again, this is backwards. Really, it should have been square root X, which is a variable name, should have been assigned, had the results of square root X assigned into it. So this is backwards as well. And the errors you get will help you understand that. And that's why you need to know L value and R value. If you see left operand must be an L value, it's not a very helpful message if you don't know what an L value is. But now that you know that an L value needs to be a variable name, this is really just saying, hey, the thing on the left of the assignment operator need to be a variable name, and you didn't use one. That's what that means. So when you read error messages, you have to learn to interpret them. And then here, expression must be a modifiable L value. And so these are the errors that you would get if you compile that code. And then this is the corrected code. X equals 5.2. Square root X, which is a variable name, is being assigned the results of square root of X. So we're going to learn about functions later, but when you can tell something's a function because it has parentheses. And so this is a function call to something called square root, and presumably it will take 5.2 and return the square root. The output of a function, often you're going to need to store that into something to use it later on. So it's not unusual to have a function that returns a value be on the right side of an assignment operator, and then a variable is on the left side. So there's a variable declarations demo that goes with this presentation. I recommend that you complete that demonstration. And that concludes this presentation. Thank you very much.